All right, the next section we are taking up in this fourth chapter is the second theorem of calculus. Now, the first theorem of calculus was the one that introduced the endpoints A to B and how you would subtract the value of the function, derivative function in terms of B, and then subtract the value of A, substituted in for your variable, most likely x. Second theorem of calculus is basically a statement that allows them to make certain manipulations in mathematics. And it's one that makes sense because we call integration antiderivative, okay, which makes derivatives technically anti-integration. So they are inverses of each other. So that's what this is saying right here. Now, f prime is, the capital F refers to the integration of function x, lowercase f, function x. And so when you take the derivative of the integration, it's like adding acid to a base. It's like adding positive to negative. They neutralize each other. So you go back to where you started, which is what this was, only now expanded to the endpoints A to x. Well, A is a constant and subtracts out when you subtract these out, and the x then is what we have remaining. So this allows them to introduce a different function using the chain rule. So an example here says find f of x when f of t is the integration from 0 to x of the cosine t dt. So if we take this and we take the integration of the cosine, it gives us the sine of t dt. So actually the dt drops out here. When you take the integration, that's gone. I should not have included that. And that will allow us to take the sine of x minus the sine of 0, which gives us the sine of x. So the function of this is sine of x. So if we were to find the values of that, which is what they're asking for in this particular problem, we just now take that value for the function of x and plug these x's, and we get these 5 answers that they're asking for. If they'd asked us to take the inverse of that, we would get cosine bt, or just cosine t as our function. So in other words, it is saying that whatever you started with in here, with whatever modification you made with this, which is what we did here, x became the t here, you would get your original function back. So since we started with the sine of t, we now end up with the sine of x with the x substituting for the t. And that's the mathematical manipulation they allow to be done. And it comes in really handy. So let's take a look at some problems here where we would use this. Or to start off very simply. Number 81, they're asking for they're giving you that the function of x, again, capital F refers to the fact that you're going to take the integration of the lowercase function. Okay? Lowercase function is t squared minus 2t dt. The thing about this here is that this number down here is a constant, and this is where the manipulation is allowed to take place. And it doesn't have to be that way. We can actually use that, which we're going to see in a later problem. But since this is a constant, when we subtract the 2 endpoints, this drops out because it doesn't change. So when you subtract the same value twice, it disappears. So we really only focus on the x here. So we replace the x for both t's here. And then this drops out when we take the integration of it. So we get t squared minus 2t. And then that becomes x squared minus 2x. And that will be the value of the original function inside the integrator. Okay? So, except now replace the t's with x's. That's the big difference. So that's what the second theorem of calculus allows us to do. The next 2 problems, same kind of situation. We're taking the integration from -1 to 4. -1 is a constant. Therefore, that part of it's going to drop out. We don't worry about the -1. We focus only on the x and replacing the x for the t. and that gives us the square root of x to the fourth plus 1. And number 85, the same thing, we have a constant here, we don't worry about it. So that means that it's going to allow us to take the variable x and replace it with t, and using the chain rule through the many steps we could use for this, but this is all shortcut stuff at this point. Understanding the second theorem of calculus allows us to do this, and so we end up with x cosine x, which was the function in t, now changed to x. All right, so how do we use this? Well, here we got some problems to take a look at. If you take a look at problem 87 on the same page, this is what we have. We're given that the function of x going from x to x plus 2 in the integration is 4t plus 1 dt. Okay? So when I integrate this, I'm going to get 4t squared over 2 plus t over 1. Now why do I have to do that? It's because I have variables in both sides, both endpoints here. So I have to go through and go ahead and integrate this, knowing that I may not end up at the back at the same thing here. That's the issue with introducing two variables as your endpoints instead of just one. It will change what we have started with right here. If this had been a 0, then we would have gotten 4x plus 1, and we would have just been done with the problem. That's not the case here. So we go ahead and integrate this, and because this is going to have an exponent of 2, we're going to divide by 2 for introduction of that exponent. This is t to the 0, so that's going to be t to the first on top, and it's going to divide by that exponent 1 on the bottom. It's going to give us 2t squared plus 2, plus t rather, with the two endpoints as x plus 2 and x. Excuse me. So this is just a matter of basic algebra at this point. Plugging in stuff. We're going to plug in x plus 2 for this and this in the left endpoint, if you will. The right endpoint, it's going to be x here. X plus 2 squared is this trinomial, and we're going to double all of that. And we're going to subtract 2x squared plus x here. When we resolve this here, this gives us 2x squared plus 8x plus 8, then the x plus 2, and then we cross out terms that can be canceled out. 2x squared minus 2x squared, gone. X minus x, gone. 8 plus 2 is 10. This is 8x, and that is the function of x in terms of these two endpoints. Now when we do the derivation of that function that we just found, we just go ahead and derive 8x plus 10, and that gives us 8 plus 0, which is 8. So the value of the derivative at that particular set of endpoints is going to give you a value of 8. Okay? Now over here it's not so bad, because now we're reintroducing the endpoint of a constant here. So that means then that the square root of t dt is going to be rewritten as t 1/2, t to the 1/2 power dt. And since we're using sine of x here, we're not going to have to subtract anything because the 0 is going to be gone. That's why we like using constants. So we're going to plug in sine of x for this, because that is the original function. And then the dt, and we have to be careful, we got to include the dt for this. And that is the derivation of the sine of x goes right there. So sine of x to the 1/2 power stays sine of x to the 1/2 power, but the derivative of the sine of x is cosine x, and that goes right there, and that product gives us our f prime, or capital F prime of x, which is the derivation of that up there in terms of x. Number 91, same kind of thing. We're reintroducing the constant here, so we don't have to go through that manipulation we did on problem number 87. We go ahead and rewrite this so that we have our two endpoints on the end like that insignia that we use to look at the direction of the problem. Nothing else has changed. But now since we're going to replace t with x cubed, that makes this x cubed squared. And then we're going to take the derivative of x cubed right here. And like I said, minus 0 because everything's going to be equal to 0 over there. And it's going to cancel out, so that's gone. So just worry about that aspect right there. X cubed squared is x to the 6th, so that stays the sign x to the 6th times. And then the derivative for this, bring the 3 down, or as a coefficient, and then subtract 1 from the exponent gives us 3x squared. And generally when we have a mixed term, we put the trigonometric part of it last. So this becomes 3x squared sine x to the 6th. Okay? So, your assignment is on page 293. Problems 82 through 92 even. Have fun.